you.
Yeah, thank you. I hope you can see and hear, see my screen, hear me well.
Yeah,
Okay, my name is Alexander Neuwirth. I'm from the University of Münster. I'm doing my PhD right now, and in the beginning, I want to thank the organizers for giving me the opportunity to show one of my projects here, and also for providing the infrastructure with BinderHub. So my topic is regarding how one handles Feynman diagrams in Python. And there are many options out there for various environments to handle Feynman diagrams and primarily draw them. So in LaTeX, there's tikz Feynman and feynmf or feynmp. I guess these are known and I won't go into detail there. On the Mathematica side, you have FeinArts and FeinCalc. Older programs, C++, used is FeinDiagram. You can open either the GitHub link or the Binder link if you want to click on these links and get more familiar with either of those. For Java, there's AxoDraw, using some AxoDraw library within LaTeX to draw Feynman diagrams, and also qgraf. Feynman is a specific library in Python that allows to draw Feynman diagrams, and older version pyfeyn 2 by Andy Buckley and others. But this didn't get some updates for quite some time, so I took the initiative and created pyfeyn 2 with some updates to it. But first, we have many options already to draw Feynman diagrams. Why did I now pick Python or did not use one of the existing one? Obviously, Python is quite easy to use and easy to maintain, and it has a rich ecosystem. So all the scikit-hep stuff, particle library or Inuit, all of this becomes easily available. And also in general, Python is quite easy to interoperate with different tools. So that, and compared to the Mathematica, it's free and open. So that's a big plus to me, at least. Starting with feynml. So feynml was also created by the people of pyfeyn first. And there I screenshotted their webpage here, and they list what is the goal of their project. They wanted to produce sort of an XML-like dialect for having Feynman diagrams represented on a computer, and this was done within this feynml project. And such a standard, to me, does not exist yet apart from this one, and this hasn't been updated for quite some time as well. But I think such a standard is very important, similar to the LHE standard for events, for communicating between computer, person, computer, and also one can send such a feynml XML-like file to another person, and they can look at it without one having to always render them and send pictures. And it's also obviously ambivalent how one draws the Feynman diagram, since the same topological content can be represented as a graphic in infinite amount of ways. So I opted for a way similar to HTML, which contains the content, and CSS to stylize this Feynman diagram, so that one gets a clear separation of what's physically relevant and what is just fancy styling on top of it. So now, what's the difference compared to pyfeyn with the new version? The original pyfeyn just used pyx as a render engine, and now I made it a bit more general so that one can go use the different render engines, so either matplotlib, the Feynman tikz, or plain text, as well as ASCII or Unicode, and also d language can be used, which is often used, at least in a computer science context, to handle diagrams. And the project is quite focused on modularity in order to allow interfacing with other tools such as the pyLHE, pyHEPMC, UFO, which is universal fun rules object, as are used, for example, in matgraph to generate events. With qgraf is a tool that allows from a model to generate diagrams very quickly. And form is an alternative to matgraph, but it's more detailed and more for very large computation where Mathematica struggles often. And all of this can easily be glued together within Python. So just some imports in the beginning. So how would we now render within pyfeyn 2 such a Feynman diagram? We have a Feynman diagram object, and we can add it a vertex or two vertices here. They get a ID assigned, but then we can add another propagator where we set the PDG ID now to 23, so a set boson, as you can see below then. And we connected a propagator with the vertices, and we need for legs here the two incoming particles, which are d bar, and outgoing we have with 11 the electrons. And this is in the background. I don't know why it takes a bit long now, but it is done using, this now is rendered using LaTeX in the background, and then the PDF gets represented here in this Jupyter notebook. There's a lot of stuff inside of this Feynman diagram object. I won't cover all of this, but there's a lot to it and a lot of options. There's also documentation available if you want to check some details, but I hope this talk will cover most of the basic stuff that might be interesting. So we can also, here in the definition, we did not set any positions, and instead the program did what it guessed to be the best placement of these vertices, which works out nice in such a simple case, but in more complicated cases, this will need some manual intervention to produce a nice looking Feynman diagram. So we can just place these vertices. For example, now we set them to X and Y position. So this width declaration is sort of like a getter-setter mechanism, but it always returns the original object as we have seen before. So we can just chain these calls sort of like in Java, if you know such generator factories and stuff. Here's one convenient function to align the legs of the outgoing particle. And now we have tikz Feynman render, which uses the tikz Feynman package in LaTeX, and here we render it. So this is the first Feynman diagram that is shown. And now we apply a function from our library scale that scales the leg XY position and the vertices positions, and we can get it bigger. And we can also save this file here. It's test3, and then we get such a PDF file that can be further used. Now we are doing everything in Python, but if we want to go and publish some sort of paper within this diagram, it might be more convenient to actually get the diagram as LaTeX. So the underlying LaTeX that was used to produce the Feynman diagrams can be obtained with get_source_diag, which then produces such a LaTeX statement that you can just copy paste and use in some diagram. There are some weird cloned vertices that are a workaround to these Feynman package not supporting 4-point vertices that point to themselves again, because tikz doesn't like lines that point to themselves. So we just produce a cloned vertex on top of it, and that works then out nicely. And what is actually rendered is the total source. So here, this is LaTeX, you have a standalone. And if you copy paste this, run it through LaTeX, you will get exactly the same PDF as was produced here. So I've mentioned that I have added a lot of different Feynman render engines. And the reasoning behind that is that they all sort of look different, but describe the same thing. And you might not know which one will look the best for you. So you can just use this all render, and it will show you each of these renders giving a different representation of the same Feynman diagram. So here is the tikz diagram. Px looks a bit different. Also, the scaling here is different, but that is nothing that is of concern for now. feynmp produces similar looking diagram. Feynman is the Python matplotlib version, which produces this diagram. The dot language produces another diagram, and they all look a bit different. And also ASCII, we can use ASCII diagrams, and that's what I will talk about next, why this is something interesting. So often, at least from a theorist's perspective, where I'm coming from, working with Monte Carlos, you often encounter calculations that include some really cryptic names like QQ bar, EEB, box Q, ZZE. And it's not directly clear what is meant with this diagram and which momentum is assigned to. So using here I'm creating one simple box diagram. Yes, it can also be rendered using the ASCII render, and this then produces what is shown here below as a string. So you can include it either if you just have a console command line tool and want to show what is actually happening, or if you want to put it in the documentation of your code so it can be easier seen what is actually happening in this calculation. You notice here some left space. This is if you want to add a momentum vector so that the name does not collide with the name of the particle. And also a bit more advanced, given you have Unicode support, you can, instead of having these dashes and angular brackets, you can have arrows. Whoops, that shouldn't happen. That's funny. Yeah, I know why it didn't. Why it happened. I did not run this one right. Yeah, doesn't matter now. Running everything from the bottom up, from the top down will work without problems. So one complicated problem with Feynman diagrams, especially more advanced diagrams, is that it's not so clear how one places the vertices of a Feynman diagram. And this automated placement of the vertices, one can often rely on spring models that then place the positions of the vertices based on minimizing the energy, but the dot language also provides formats, for example, the dot, which is sort of a flow graph-like structure of the vertices, then or Nito, which is a spring model, but I've also written my own placement algorithm, which is sort of like a van der Waals force, which makes sense because you have some repulsion, so vertices don't overlap, and some tension between the strings to keep them together. And then, in this case, in my implementation, I use Imminuit to minimize the energy. So if we now, for example, use qgraf and generate ourselves a diagram, which is a neutrino, electron neutrino to another neutron electron neutrino. We first have to compile qgraf, and it runs in the background, but that should be quick. Then we get 404 diagrams, and looking at the third diagram, this does not get rendered well by default, but using some intermediate Feynman diagram function, we can use the Feynman adjust points function, which uses the dot language to arrange the vertices based on a spring model. And you can see that this, now one can at least see what is happening between these propagators, but it's not so nice that it does not retain the symmetry of the Feynman diagram as one would have drawn it by hand ourselves. So the alternative is to use this auto van der Waals formalism that I talked about. It also does not look so well, but it looks a bit flatter. And the way to solve this is now we force the points to go onto grid points. So on every grid point, for example, here on a grid with 5 points in X, 2 points in Y dimensions, on every point only one vertex a vertex can be placed, and then we get, in this case, not necessarily the best, but here we can already get a better diagram. We see some good, almost all vertices are placed as we would have done if we draw it by hand, except for this last one. We can just look in the Feynman diagram at the vertices, and we have the x and y values here given. So we can just give our vertex we can just shift this one vertex by 1 point, and then we get a Feynman diagram that I think already looks quite well compared to the initial attempt. We can also look at another diagram, which is already shown below. Given the time constraints, I won't go through all the toggles, what's happening here, but you can see that we have two propagators connecting the same vertex here, so we have to bend them in order to avoid them overlapping. This is what this auto bend does. Then we put them on a grid again, and we align the vertices, and out comes this diagram. So some manual intervention is needed, but works quite nicely, quickly. For this auto van der Waals function, I also have some extra punish parameters where you can punish the minimization procedure or give it some bias to keep the X symmetry of the vertices, Y symmetry, or if you want to punish it for overlapping Feynman, overlapping propagators, so if they are crossing each other. But for some diagrams, it's inevitable, so you always have some intersections. I've previously talked about the feynml project. So here I'm again doing sort of a Drell-Young-like process, and then we can print it as XML and export, import, whatever, use it with different tools. Again, like HTML, we have some metadata covering the versions as well as diagrams, which can be multiple diagrams, and the propagator has the property of which vertices it's connected to, and the vertex is just a standalone point. So we don't have a redundancy between vertices also containing which propagators they are connected to. A bit advanced, and I will only touch it very briefly, the styling, you can customize it using some CSS as you like. For example, here, I want to have my lines bent to every object should have a bent direction to left, color green, and we can also add some other CSS rules. So classes are red. So here I have some with class where I set the particle to not red. So that would be not red class, and I set its color to blue. I can just target some ID. I can target every particle with given PDG ID or by another ID again. This is then also contained within this feynml, and if one renders it, this kind of weird looking graph comes out. And the convenience of this CSS formalism is that you can just write your style for one diagram for once and use it on multiple diagrams. So in this case, I have a very non-physical diagram, which you can see below. And here I can first remove all of this CSS stuff, and I render all the diagrams within the feynml object that I create here. And I have two diagrams. One has the 6 leg set to orange color. And now if I add these CSS rules, they can get quite complicated. So I want every fermion now to be represented by the line of the gluon, while this is obviously a weird use case, but it might be convenient to switch between normal line and Higgs lines and ghosts, and there are enough cases where one might actually change some line of a particle. Also, one can use this modern CSS not prescription. Yeah, look through it on your own if you are more further interested in it. Okay. So I started with saying that modularity is quite important. So I will talk a bit about interfaces. I guess most of you know the LHE standard, and within such an LHE file I printed here, we have an event with multiple particles and their momenta. And this can be loaded using the pyLHE, and then one can print these events. No, it did not keep them here, so I'll just show them again. So in this case, we have first UG going to Z0 and U, and the Z boson decays to electron positrons. And here we have charm, anti-charm process. This is the default representation within feynml and pyfeyn. This can be also rendered as such a Feynman diagram. While this is again not physical, since the hard process is culminated here into one point, it still offers other graphical way to look at these LHE files. But also it's a bit more expensive to compute. The pyHEPMC allows for HEPMC files to be rendered. In this case, due to Docker and binder or whatever, the rendering via dot did not work out of the box, so I saved it from my local run. And here I have a big HEPMC file where a lot of stuff happens in a proton-proton collision, going to a photon and a lot of other stuff. And this one can also run with some customization of the color here through pyfeyn, and then we can get such a representation where you see the green lines are the protons, the red lines are again the hard process, as can be filtered by the status codes in HEPMC, and this file is very big. And another way to generate diagrams is via the UFO I talked about previously, the UFO models. They define all the vertices of the model and also how they are defined mathematically. So using the UFO draw package, which is also sort of set up as a command line tool to draw from a UFO file the Feynman diagrams. Here I want to look at anti-electron neutrino and electron neutrino, and also tau in the final state. So I just generate these diagrams with the UFO draw function, exclude some weird ghosts just for demonstration purposes. And then we can see here 25 diagrams. They are not necessarily yet perfectly looking, but it offers a good insight into what is happening out of the box. And I'll close this. So what's another very new and experimental package that I started is feynmp, that now aims to convert these feynml definitions of a Feynman diagram to a Feynman amplitude and further compute it. So this is just a demonstration what could become possible also in the future with it then. So here again, I'm looking at a triangle-like diagram, dd bar going via gluon to uu bar. I assign them some momentum here, and I can add this rule, but I can also do it object-oriented onto the Feynman diagram instead of via this CSS formalism. I plug in the missing momenta, so I just defined PA, PB, KA, KB, but I did not give the propagator which momentum it has, so this gets added here. It's PA plus PB, and this is then plotted here. And often in theory, we need the conjugated diagram to square it. So this is then here represented. Now the UU bar is initial with its momenta, and dd bar is now the final, and we can combine these diagrams to obtain the scrapped matrix element. So now we need the model in order to plug in the Feynman rules. So this would then be this lengthy expression, which is a string to allow for easy manipulation compared to, for example, Mathematica. We get some expressions that we want to run in formcalc. We apply them, run it through, convert the result to sympy, and show it and compare it against here, for example, Alice Sterling book, or what FineCalc has done on their web page, and we obtain the same result as a cross-check. For more complicated stuff, this is still a work in progress, but it works, and it's, I think, convenient to have everything in Python, or at least working in Python and gluing everything together. Since I'm very close to the end, I just want to show here one overview of what I've demonstrated. I've shown you the pyfeyn project to draw these diagrams, which uses the feynml to define the diagram. And this provides the interfaces to all sorts of external renders or interfaces. And also UFO Draw allows to generate diagrams via feynml that uses the external provided UFO. And feynmp, again, using form or sympy, can compute these diagrams. And this is going to be expanded in the near future. So given I'm close to the end, some interesting points that I still have open are listed here. I think the most interesting one is adding more attributes and getting box calculations running, and maybe join up with scikit-hep if there's an interest for that. Thank you, and you can also open issues if you have questions later on GitHub. That's very easy for me. Thank you.
Thank you very much, Alexander. Very impressive. Very impressive. I could have plenty of questions, but I'll let the floor to other people if they want to raise your hand. Anybody has a pressing question? We still have a few minutes. Yeah, Angus?
Hi. Yeah, really impressive, interesting library. From the Jupyter side of things, have you considered integrating the IPython display protocol so that you don't need to call render on these diagrams for them to be rendered in a notebook?
Oh yeah, that's implemented, yes. Here in the first case, I have
Did I miss this?
This one,
oh,
right?
I missed it. I looked in the source code and I couldn't see it. No, that's fantastic. There we go.
Yeah, it's at the very bottom.
Fantastic. Cool. Thank you very much. That answers my question.
You're welcome.
Right, since people are still a bit shy, no worries, we have time. So let me ask one question. Okay, so I understand why you try to put everything together. One practical question: you have a huge amount of functionality here, more than you can intake in 20 minutes, certainly. Is this presentation actually now the biggest documentation, or you have a big set of examples and stuff in your package? I didn't check yet.
Yeah, I can show it.
Because you know that typically, especially for these kinds of things, when they get complicated, people go and find examples and then they adapt to the use case, right?
Yeah, I have sort of a support matrix here for the different attributes for the given renderer, because, for example, the style, not all of the renderers necessarily support everything here, so it's a work in progress, adding step by step more stuff depending on the demand, and primarily support is for tikz as of now, because I think it's the best fundament.
All right. I see you already, Jim, so I will stop with my questions because you give the chance. Thank you. Jim?
Follow up to that one. So you got that support matrix. Is there a difference between can't support and can but have not implemented yet?
No, it's just what is implemented. I don't think there's much that cannot be implemented in any of them, but
okay.
Yeah.
Right. Do you have people helping you already, or you are a single team, a single person team?
I'm doing it solo as of now.
Okay, so this started as usual as a pet project, and then it evolved to something actually quite non-trivial anymore.
Yep.
No point taken. Thanks. In the interest of time, because I see it's just about the time to finish the nominal 30 minutes, I'll move forward. But by all means, get in touch with Alexander if you are interested in anything particular, be it a special diagram or a backend or something, or front end, so to speak. Yeah, thanks again very much. Very nice.